Okay, in question 5, part B, we're supposed to verify that this differential equation is exact, and then we need to solve this differential equation, right? So, okay, let me do that. Um, so how do I verify that this differential equation is exact? So basically, the logic um, is that whatever the coefficient in front of dx, it should be the derivative of some unknown function with respect to x. And the coefficient in front of dy, it should be the derivative of some unknown function with respect to y. So in order to verify that such an unknown function does indeed exist, we need to differentiate the coefficient at dx with respect to y, and the coefficient at dy with respect to x, and these two should be equal, right? So this is kind of like m, and this is like n. So the m differentiated with respect to y is going to be, well, what is it? It's minus 2x over y squared plus, well, cosine x does not depend on y, so e to the y sine x. So let's differentiate it. So e to the y sine x times the derivative of y sine x, which is sine x, times y times cosine x, plus e to the y sine x. Now I'm differentiating y is just 1 times cos x. Okay, that's it. So now n, the derivative of n with respect to x. 1 over y squared differentiated with respect to x is just 0, so minus 2x over y squared plus, now I've got to differentiate this whole thing with respect to x, and this is going to be like e to the y sine x times y cosine x times sine x plus e to the y sine x times cosine x. And these two are indeed equal. Okay, check. So this differential equation is indeed exact. So now let us solve it. So to solve it, we need to find the potential. And if, you know, the coefficient in front of dx is the derivative of u with respect to x, then in order to find u itself, I've got to integrate it with respect to x. So to 2x over y plus e to the y sine x y cos x dx. I mean, sound looks scary, but as a matter of fact, it's not really that scary. So I am integrating with respect to x. So y is now a constant. So the antiderivative of 2x is just x squared, right? So it's going to be x squared over y plus, and here notice that y cosine x is just the differential of y sine x. So this is, its antiderivative is just e to the y sine x, right? So which is not so bad, right? So plus some constant, but this is not exactly constant, plus some function of y, because uh, you know, so with, for every value of y, it is a constant, right? So but it could be a different constant for different values of y, so it should be a function of y. All right, so now how do we find this c of y? Well, we also know that the partial derivative of u with respect to y is this n, right? So now let us differentiate u with respect to y. So this is minus x squared over y squared plus e to the y sine x times sine x, and this is supposed to be equal, well, sorry, plus, of course, plus c prime of y, plus c prime of y. And this is supposed to be equal to 1 minus x squared over y squared plus e to y sine x times sine x. Okay, so this term cancels out, minus x squared cancels out, so we get a c prime of y is 1 over y squared, so which implies that c itself is going to be the antiderivative of y squared, which is minus 1 over y. Okay, so now let me just to save space and time, replace c with its value that we just found, so minus 1 over y. So this is the potential, and the general solution is that the potential equals y. So this is the potential equals a constant. So this is the general solution. Now, if it is possible, then it is recommended to solve for y, but here it's not possible. It's hardly possible to solve for x too, so we'll just leave it as is.